Okay, so in previous class we discussed static RAM and dynamic RAM. So in static RAM, for storing 1 bit of information you will be requiring 6 transistors, so it is less denser. When compared to dynamic RAM, you will be requiring only 1 transistor and 1 capacitor for storing 1 bit of information. So because of that, it will be more denser and it will be cost effective, right? Because less number of transistors, then it will be cost effective. Then coming to speed, static RAM will be much faster compared to dynamic RAM. So because of that, this will be employed in your cache memory, right? One disadvantage with respect to dynamic RAM is that you have to refresh that circuitry again and again, because in dynamic RAM, your information will be stored in the form of charge, right? In capacitor that will be stored, but as your time passes on, so it will be leaking of the charge. So for that purpose, you have to keep on refreshing that circuitry. So that is done with the help of a DRAM controller. So that is the disadvantage with respect to DRAM. Then we discussed memory sharding. Another concept in embedded system discussed was memory sharding. Memory sharding means, you might have heard of this BIOS, basic input output system configuration. So in this, you will be storing the configuration information, right? Configuration of your serial port, then other devices, all those information will be stored in your BIOS ROM. But accessing data from this BIOS ROM will be taking more time, right? So it will be varying in the range of like 120 nanosecond to 200 nanosecond for accessing data from ROM. So instead of that, what people will do, means the designer will do, they will create a RAM that will be sharing the same address as that of your BIOS ROM. So that we call it a shadow of your ROM, right? So during boot up, what happens? Instead of reading data one by one on data from ROM, entire ROM image will be given to your RAM during boot up time, right? So from after that, you will be disabling your ROM access and you will be write protecting the RAM. Then you will be accessing one data from your RAM memory, because accessing data from RAM memory will be much faster way, right? So that is the memory sharding concept. Then we discussed embedded selection, right? So memory selection for your embedded device. So here, depending on your application requirement, you will be selecting the memory. So you'll be requiring memory like program memory, data memory, and some other memory for storing some lookup table, etc. So this program memory wherein you'll be storing your application code. But for simple application like electronic toy, you may not be using some embedded operating system or real-time operating system. So memory requirement for such cases will be less. So you can use on-chip memory that is part of your microcontroller. So depending on application, you will be selecting this memory. Two parameters you have to keep in mind while selecting memories. One is size of the memory, means you will be having some standard size memory. Yesterday I told, like for 750 bytes of memory requirements, you will not be getting 750 bytes memory. That particular specification you will not be getting, because you got some standard size memory like 512 bytes, 1 kilobyte, 2K, 3K, and not 3K, 2K, 4K, 8K. Like that, you'll be having different standards. So for 750 bytes, you have to have like 1 kilobytes of memory. And another is word size and your data bus bit should match. If your controller or processor can access 8 bit of data, then you have to match that with your memory. This one, how much memory you can access in one time, right? So those two parameters should be considered. Then we started with sensors and actuators. So through sensors, we will be getting data to system. Yeah, screen is not visible because I am not shared it. I am recalling the previous class concept. Screen is not visible to anybody, right? Don't worry, I haven't shared the screen. I'm recalling the previous class concept. Is it clear? Screen is not visible. I haven't shared screen. I'm recalling the previous class concept. Okay. So sensors and actuators. So they are nothing but transducer. Example of sensor is like your temperature sensor. So it will be sensing the temperature and it will be given to your embedded system for like processing or controlling that one. And actuator is nothing but it is an output device like your stepper motor. Means both will be converting energy from one form to another. Then we discussed IO system. So we will be continuing with that one wherein we discussed LED, light emitting diode and 7-segment display. So we will be continuing with from that point. So now I will be sharing the slide. Now you people can see the slide, 7-segment display. Can you see the slide now? Yeah, one of you can message me. Okay, okay, yeah. So this 7-segment display, again, this is an output device used for giving some value, for displaying some value like alphanumeric value. You can display some alphabet or you can display some numbers on this 7-segment display. So it consists of 8 LED, light emitting diode. So this each segment is made up of one diode. So we'll be having this 7 segment and this another one is dp, decimal point. So you will be having 8 LEDs, right? So this is used for displaying some alphanumeric character. So here you will be getting in two configuration. The 7-segment display will be coming in two configuration. One is common anode and another is common cathode. So in common anode, what happens? All the anode will be connected to one common point. That common point will be VCC. And in order to forward bias this diode, you have to apply logic 0 to this cathode, right? These are cathode and these are anode. So in order to forward bias this one, this is at logic 1, that is 5 volts, and this should be at logic 0, that is 0 volts, in order to forward bias this diode, right? So that is common anode. Common cathode means all your cathode will be connected to one common point, that will be ground. So these lines will be connected to your port of some microcontroller. So you have to write 1 to this line so that your diode will be forward biased and it will be conducting. So common anode, common cathode. So the same thing whatever I explained, the same thing is there. Then next we will be seeing optocoupler. So this is the solid state device used to isolate two parts of circuit. So assume here you got some high voltage circuit. So you don't want to directly interact with that high voltage circuitry. So what you will do, you will make use of this optocoupler, right? So this will be isolating two circuit, two parts of your circuit, right? This is the high voltage. You need not to operate that directly. So for that purpose, you'll be making use of this optocoupler. So this optocoupler consists of LED, that is light emitting diode, and photo transistor, right? So this is photo transistor and this is LED. Both will be combined in one a single package or single housing. So this thing will be in one package. So what happens when you apply current to this one, when you give supply to here, so this diode will be conducting. So when it conducts, it will be emitting light, right? Light emitting diode. So it will be emitting light, right? So this light will be absorbed by your this transistor. This is photo transistor, right? It will be able to detect that light and it will be getting that one. In turn, it will be turned on. So by this, you will be controlling this part of circuitry. So you are isolating. There is no connection between your this part and this part, right? So this is used for isolate two parts of your circuitry. And other users of this one is like in suppressing inference in data communication, circuit isolation, high voltage suppression, etc. So these are the different application wherein this optocoupler is used. So optocoupler can be used in either input circuitry or in output circuitry. So there are different companies who are into manufacturing of this one. This IC from Fairchild Semiconductor is an example of an optocoupler IC. So next you'll see relay. So relay is an electromechanical device, right? So you can see it's a switch. So here in embedded application, the relay unit acts a dynamic path selector for your signal or power. Dynamically, you can change the path of this one, that signal, whether you want to select power or you want to select some other thing, right? We'll be discussing this done. So here this relay unit contains a relay coil made up of insulated wire on a metal core. Means you will be having a metal core, on that you will be having insulated wire and a metal armature with one or more contacts. So this relay coil, so here you will be having different type of relay coil. So this will be working on the principle of electromagnetic, right? So it relay works on electromagnetic principle. Means when a voltage is applied to the coil, current flows through that coil, so which in turn generates a magnetic field. So what happens when magnetic field is generated? Then the magnetic field attracts the armature core and moves the contact point, right? So in this way, you will be moving the contact point. So when the movement of contact point changes, then power signal flow path will be changed. So here, this is a relay coil, and this is your armature core. That is, when you pass current through this coil, it will be generating magnetic field. So when magnetic field is generated, then this will be attracted. Means you will be closing this path. So it will be closed. Getting so dynamically you will be changing the path, right? So you can say it is a switch. It will be acting as a switch. Then now can you see the slide? Can you see the slide now? It got disconnected and again I am connected it back. Okay. So here you will be having single pole and single throw normally open. So this will be normally open. When you energize this coil, this will be closed. Then another type of this one is single pole, single throw, normally closed. So this will be normally closed. But when you energize this one and this coil, then again this will be open. In other configuration, you got single pole, double throw. So you'll be having these two double throw. Right? So when you energize and de-energize a coil, you will be either connecting to this path or this path. Yeah, you got the different configuration. One is normally open single pole, single throw relay. The circuit is normally open and becomes closed when the relay is energized. Next one, normally closed single pole, single throw relay. The circuit is normally closed and becomes open when the relay is energized. Then another one is single pole double throw configuration. There are two paths for information flow. They are selected by energizing the de-energizing the relay. But we discuss same thing. Then you'll be having some driver circuitry for this one, right? The relay is normally controlled using a relay driver circuit. So this driver circuit is directly connected to port pin of your controller or processor. So you'll be writing some data on this one. Means you will be controlling this transistor. When this transistor is turned on, you can say the current will be flowing through this coil. So when the current flow through this coil, then this coil will be generating magnetic field. So when magnetic field is generated, then this path will be closed, right? So this is controlled through your port pin of microcontroller or microprocessor. So this transistor will be acting as a driving circuit of this relay. And this is another important point you have to remember, this one freewheeling diode. the use of this freewheeling diode is to protect your relay and this transistor. So when you turn on this transistor, current will be flowing. So when you turn off this transistor, suddenly there will be reduction in the current flow. So because of this reduction in the current flow, there will be a large voltage that will be generated in reverse direction. So this may damage your relay and transistor. So for that purpose, you will be providing this freewheeling diode. So just remember, this freewheeling diode is essential for protecting the relay and transistor, right? So next, one more output device is buzzer, right? So this buzzer is a piezoelectric device for generating audio indication in embedded application. So it will be giving some indications, right? So here it consists of a piezoelectric diaphragm which produces audible sound in response to the voltage applied to it. So when you apply voltage to this buzzer, then it will be producing some audible sound. So you'll be having some this piezoelectric diaphragm. So that will be producing audible sound. So here you will be having two types. One is self-driving and another is external. So self-driving means if we give some, if we apply some voltage to this thing, then it will be producing some tone, predefined tone. So you'll be getting one predefined tone when you apply voltage to this buzzer, which this is self-driving circuit type of buzzer. Another is external piezo buzzer. So here, if you vary the applied voltage, then you will be getting different tones. So that is the difference between self-driving and external driving. So in self-driving, you will be getting one predefined tone on applying the voltage. But here, when you vary the applied voltage, right, then you will be getting different tones, right? So next, push button switch. So this is an input device. So when you push the button, then you will be contacting that one. Here you will be having two types. One is push to make and another is push to break. Means you will be having two types. Push to confirm, the switch is normally open state and it makes a circuit contact when it is pushed or pressed. So when you press the switch, then you will be closing that path, means there will be a connection. Then it will be normally open, push to make. Push to break means it will be normally closed. So when you press the switch, it will be opening, right? So it breaks the circuit contact when it is pushed or pressed. So push button stays in the closed, that is push to make, or open state as long as it is kept in that push state, and it makes or breaks the circuit connection when it is released. So when you press the switch, either you will be making the contact, means you will be establishing the path, or you will be breaking that one, right? This is an input device. So here this is, you can see the switch. So when you press this switch, you'll be establishing these connections. So it will be used for generating a monetary pulse, right? Push button is used for generating a monetary pulse. So in your embedded application, push button is generally used as a reset and start switch and a pulse generator. You might have seen your embedded controller lab so many switch buttons, right? So when you press that one, you'll be generating some pulses. So based on that, you may be controlling some other output devices like relay, buzzer, etc. So connected to port pin. So this push button is normally connected to port pin of your host controller or processor. So depending on the way in which a push button interface to controller, it can generate either a high pulse or low pulse. So depending on how your this is connected, right? So figure illustrate how the push button can be used for generating low and high pulses. So here will be a low pulse generator and this will be high pulse generator depending on how the pin is connected. So here port pin is connected here. That is the, depending on the how this pin is connected to your port, based on that you will be generating higher low pulses. So next we will be seeing communication interface. So here in this communication interface, you will be having onboard communication and external communication. So onboard communication means in your embedded application, you'll be having so many subsystems or so many IC part of your single PCB, right? So on a single PCB of your embedded system, you'll be having so many ICs. So communication between these IC, we call it as onboard communication, right? Communication between the components of an embedded system, that is known as onboard communication. And you have to, in some cases, you have to interact with the external product or some other external system. So communication between the embedded system and some external devices, that we call it as external communication. Is it clear? You will be having onboard and external communication. Onboard communication means communication that is taking between different IC of same PCB board. Your embedded system will be having so many ICs, so many small systems you can say, right? So in order to interact between this IC, you will be requiring some communication buses. We'll be discussing all those things, right? That we call it as onboard communication. External communication means your embedded product will be exchanging information with some other external devices. So that we call it as external communication. So for onboard, you'll be having different buses like I2C, inter-integrated circuit bus. Then you'll be having SPI, serial peripheral interface bus. Then you'll be having one wire bus. Then you'll be having UART. So many buses are available for this one, right? So we'll be discussing all those things detail. Okay, same thing, whatever I explained. Communication interface is essential for communicating with various subsystems of embedded system and with the external world. So there are two types. One is onboard communication interface and second one external communication interface. So onboard means device or board level communication interface like serial interface like I2C, SPI, UART, one wire, and all these things comes under this onboard communication interface. Onboard means you will be exchanging information with the ICs that are part of same board, same printed circuit board of your embedded system. So external communication interface means product level communication interface means your embedded system will be interacting with some other external device. So that we call it as external communication interface. So you got different protocols. This one, buses like wireless interface, like infrared, Bluetooth, wireless LAN, radio frequency wave, GPRS, and RS-232, Ethernet, USB, etc. So many external communication interfaces are available. So, an embedded system is a combination of different types of components or chips arranged on a printed circuit board. So, just now I mentioned, onboard communication interface refers to different communication channel buses for interconnecting the various integrated circuit and other peripherals within the embedded system. Right? Whatever we discussed. So, you got different interfaces like SPI, I2C, UART, one wire, parallel bus, etc. So we will see first one, inter-integrated circuit. This is pronounced as I2C. I2C. So this is a synchronous bidirectional half-duplex two-wire serial interface. Half-duplex means either you can transmit or receive at any given point of time. It is not like simultaneously you can send and receive the information. Either you can transmit the information or you can receive the information. So it is half duplex. And here we will be requiring two serial wire. One is SCL, that is serial clock line. Another one is SDA. One is serial clock line, another is serial data line. So this serial clock line is responsible for generating the clock pulses, right? So SCL line will be providing the clock to your components connected to these buses, or you can say here will be a master slave concept, right? So this master will be generating the serial clock, and this SDA line, serial data line, is responsible for transmitting the serial data across the devices, right? So this I square was developed by Philips Semiconductor in the early 1980s, right? So the original intention of this I square was to provide interface between your microcontroller and peripheral chips in the television sets. So for that purpose, it was developed, right? So I square C is a synchronous. Synchronous means both your transmitter and receiver will be synchronized to the same clock pulse. Bidirectional means you can send and receive data, but half duplex. Half duplex means either you can send data or you can receive data. Right? Two-wire serial interface bus. So you'll be requiring two lines, two wire. One is SCL clock, another is SDA line. So through this line, you'll be sending the clock pulses, that is for synchronization purpose. And SDA line is responsible for transmitting and receiving the serial data. So continuation of I square C is a shared bus system to which many number of I square devices can be connected. Right? So this is a shared bus. So you will be having two lines, that is one SCR and SDA line. To this shared bus, you will be connecting so many devices. So here we will be having concept known as master or slave. So devices connected to this I square bus can act as master or slave. So master is one who will be controlling the communication, that is initiating the establishing the communication or initiating the communication and terminating the communication, then sending data, generating synchronization clock pulse. All those will be done by your master, right? Slave means it will be either sending or receiving upon the request by master, right? So master slave device can act as either transmitter or receiver, right? Regardless whether master is acting as a transmitter or receiver, the synchronization clock signal is generated by master device only. Just now I mentioned, so master will be responsible for generating the synchronization clock pulse. So here it is shared bus. To that shared bus, so many devices can be connected, right? So they can act as either master or slave. So master is the one who will be initiating the data transfer, or who will be terminating that one, and who will be sending the synchronization clock pulses, right? So slave device, they can send data, receive data depending upon the master's request, right? So here I squares support multi-masters on the same bus. Multi-master means on same bus so many devices can be connected. So you can have more than one master on this system, this interface. So here you can see one is SCL line, that is serial clock line. This is another serial data line. Two wire I square C bus. To this bus, you can connect any number of devices, right? So here, your controller or microprocessor is acting as a master, and you got two slaves. Slave one, that is your E square from memory, and another slave two, another device that will be connected to this bus. So this master will be one who will be responsible for establish or giving the clock signal to this slave. So if this master wants to communicate with slave one, then it will be sending the address of this slave one on this bus, right? So this information can be accessed by all the slaves connected to this system. So it will be comparing this address with its own address. If there is a match, then this will be responding to that information, that address, right? So then master, based on it requirement, whether it wants to send data from this master to slave one, or it wants to access data from slave one to master, based on that, if further information transfer will be taking place. Here addresses will be hardwired for each devices, right? So each devices will be in some particular addresses, that is hardwired, that you have to remember, right? We'll see the process how the data will be exchanged. So here I square bus is built on input buffer and an open drain or collector transistors. So The bus is when the bus is in ideal state, this transistor will be in the floating state. The output lines switch to high impedance state, right? So those two lines will be switched to high impedance state in ideal state, right? When the bus is not doing any transfer. So during that time, your output line, this SDA and SCL, switch to high impedance state. For proper operation of this bus, both the lines should be pulled to supply voltage. Means 5 volt for TTL family and 3.3 volt for your CMOS family using pull-up resistors. So pull-up resistors of value 2.2K is provided, that is connected to your lines here. Here you can see. So through this, you have to bring this line to SCL and SDL line to this supply voltage to this pull-up when you want proper operation of this one. When this bus is idle, it is not doing any data transfer. That time it will be high impedance state. It will be putting the high impedance state. So for proper operation of this one, they should be pulled to supply voltage depending on whether you are using TTL family or CMOS family. Right here, just now I told address of I2C device is assigned by hardwiring the address lines of the device to the desired logic level. So done at the time of designing the embedded hardware. Right? At the time of designing the embedded hardware, this address will be hardwired. Right? Each device will be having some address, and that will be hardwired to those device lines. Here, the sequence of steps you can see. The sequence of operation for communicating with an I2 to slave device. First, the master pulls the clock line SCL of the bus to high. So this will be the first step. Then after that, master device pulls the data line low when the SCL line is at logic high, right? So this indicates the start condition for data transfer, right? So when master wants to initiate this data transfer, then first step what it will be doing, it will be pulling this clock line to high, clock line of your bus to high. Then it pulls the data line to low when your SCL line is at high position. Right? This is nothing but start condition for data transfer. Then the master device sends the address, right? Address of the slave device to which it wants to communicate over the SDA line, right? Then it will be putting address on this SDA line. First step, it will be pulling your SCL line to high. Right? When SCL line is high, then it will make SDA line, that is data line low. So this is nothing but indication that master wants to start communication, that is start condition for data transfer. Then after that, it will be putting the device, slave device address onto your SDA line to which it wants to communicate. Then clock pulses are generated at the SCL line for synchronizing the bit reception of the slave device. So first it will be sending the MSB of the data is always transmitted first. So the data in the bus is valid during the high period of the clock signal. Then next, the master device sends the read or write bit, whether it want to read data from slave or it want to write data to slave according to the requirement. Then the master device waits for the acknowledgement bit from the slave device, whose address is sent on the bus along with the read write operation command, right? So first, then it will be sending the this information whether it want to write or read. Read means it will be sending one value, bit value one, and write means it will be sending 0. Then it will be waiting for the acknowledgement from the slave device, right? Then slave device with address requested by the master device responds by sending an acknowledgement bit for the SDL line. Then once the slave receives the address on that SDA line, it will be comparing with its own address. If there is a match, then they will be responding to that request, whether it wants to responding to that one by sending an acknowledgement bit over the SDA line. Upon receiving the acknowledgement, the bus master device sends the 8-bit data to the slave device or SDA line. If the requested operation is write to Yeah, can you see the screen now? Can you hear me? It got disconnected. Is it okay? Can you see the slide? Can you see the slide now? Okay. So, upon reaching the acknowledgement, depending whether master wants to read data or write data, based on that, it will be reading or writing data through the slave. Then the master device waits for the acknowledgement bit from the device upon byte transfer complete for write operation and sends an acknowledgement bit to slave device for read operation. Means here after each byte of information is transferred, then you will be sending or receiving the acknowledgement depending on the transfer. If master wants to write data to slave, then after sending one byte of data, it will be waiting for acknowledgement from the slave device. If master is receiving data from slave, then after receiving one byte of data, it will be sending an acknowledgement to slave saying that it has received the data. So this is an important mechanism that is available in your ISPAC, that is acknowledgement, right? That will ensure that data is transferred properly. So these are the steps involved in transferring data and receiving data from this one. So just I will recall this one. First, the master pulls the clock line to high. When the clock line is high, that time it will be making this SDA line low. So it indicates start condition for data transfer. Then the master device sends the address on this SDA line. Right? All the devices connected to this bus will receive this address.